I'm Anthony.
I'm Michael.
I'm Mary Lou.
I'm Solomon, and our project is on scaffolding for central nervous system regeneration.
The central nervous system is quite literally the backbone for everyday human biological function. Each year it is said that around 250,000 to 350,000 Americans live with and suffer with spinal cord injuries, and that number only increases every year. These injuries can be extremely debilitating and permanent, causing the loss of sensation or even the loss of function in the body. And this is due to the fact that nerve repair and regeneration inside the central nervous system is pretty poor. These kind of injuries can put a huge financial burden on a person. Statistics show that becoming a paraplegic at around age 30 can cost someone up to $2.5 million. The audience for our kind of a device would be for manufacturers, researchers and doctors, and most of all, the patients who suffer with nerve damage.
So our approach to this need will be through the implantation of a nanofibrous hydrogel network, which will be made from hyaluronic acid with the hopes of inducing the generation of new neurons and repair of axonal damage. We will be utilizing a electrospinning technique in order to create the nanofiber networks with hopes of creating increased total surface area in order to provide more attachment for the cells. The material chosen was hyaluronic acid due to the fact that this material is naturally abundant within the neural extracellular matrix and has been well characterized in terms of contributing to cell adhesion and survival. Additionally, the material can be easily modified in terms of its mechanical and structural properties. For example, through cross-linking, you can modify the degradation rates as well as the various mechanical properties such as specific modulus or compressive strength values as shown up there. One of the most important aspects of our approach will be through the seeding of NSPCs due to the fact that these are able to differentiate into either new neurons or oligodendrocytes. Additionally, we hope through the incorporation of synthetic laminin derivatives that this will help to increase the adhesion of the NSPCs and their interaction with the hydrogel itself. The final aspect of our approach is through the incorporation of a nanoparticulate drug delivery system, wherein neurotrophin-3 will be delivered locally through its encapsulation within polymeric nanoparticles. This was chosen due to the fact that NT3 is a very important growth factor in terms of neural differentiation and survival, and additionally, polymer nanoparticles can be easily controlled in terms of degradation rate. As you can see, this is the basic workflow from fabrication all the way to degradation. This incorporates incorporation of the nanoparticles as well as seeding from the patient nerve tissue onto the actual hydrogel itself. The most important thing to know on this workflow is how the nanoparticle itself will be cleaved from the hydrogel. This will be done through naturally occurring enzymes known as esterases, which are found within the neural environment. And so once these nanoparticles are released, they will be able to interact with the NSPCs in order to control differentiation and restore the lost axonal connections.
So from a cost-benefit perspective, our solution carries a lot of the same costs as the existing solutions on the market, which include surgery, as well as other treatments to help with the patient's recovery. These can be relatively expensive, ranging from $14,000 to $30,000 in total costs. The benefits, however, are that the nervous function is restored after the surgery and the recovery process. So they're in removing the lifelong costs and treatments that are associated with that, which include things like wheelchairs and maintenance, which can cost thousands of dollars every year, physical therapy, as well as other treatments and medications, totaling to a lifetime cost, as Mike mentioned, of $2.5 million per patient. Ultimately, they're restoring their quality of life and removing those lifelong costs.
Okay, so currently we have found different types of materials that have been used for research using hydrogels in neuron regeneration. Some of these include extracellular matrices of central nervous system tissues such as brain or spinal cord tissue, hyaluronic acid, and other peptide modifications to increase cell adhesion. Through the research that we found, there have been many benefits for using a hydrogel scaffold, such as increased cell adhesion, good differentiation, and also good host cell response. However, from the ones that we did find, there were some limitations such as a quick degradation time of around 3 weeks, which can affect the growth of the neurons. And also, different materials are affected by the concentration of protein in cells that were injected and can cause a negative cell response. So how our hydrogel is different than the previously found ones is that we want to address the degradation problem by increasing cross-linking, and we want to try to get the target time to 12 or more weeks to ensure that all the neurons are growing. We also want to utilize hydrogel's drug capabilities, and to do this we want to incorporate a drug that might prevent long-term inflammation, which could cause problems in the body, and also utilize the encapsulated growth factors to ensure that they are staying as long as we need them to ensure self-growth.
That was our presentation. Thank you for listening. These
Thank
are our
you.
sources.